In the present video, we're going to present function fit from the Maxima plugin and some related functions that will help us determine the least square fitting of some data with respect to some functions. So we're going to start by looking at this spreadsheet or worksheet. The function fit includes 6 arguments: expression, and a number. First the data, then is a list of variables, then is the function that we're trying to fit, then the parameters on the function, initial values for those parameters, and a tolerance. And this is going to return the values of those parameters. See an example, let's look at this made up function. A function that combines sine of x with ln of x. We made up that function, and we have created some x data. This is just simply a range that I type as range 1, 6, 2, or the other 2 is not necessary in this case because we're all 1 by 1. So we got the number from 1 to 6. And then I'm going to calculate the function y. These are the y values in which I'm going to vectorize the function f for the vector xx. So that's going to give me exactly the result for this function. But I'm going to add some random numbers multiplied by 2 to modify these values so that I'm not actually getting this exact function, but something similar. These are the values of y corresponding to that. If I put them together by using the function augment, I could plot it in an xy plot, and it shows those points all over the place. That's my plot of the data. So now I'm going to try to fit the function to the type of function that I originated with: a plus b times x sine of x plus c times ln of x. But the way I need to do is making y minus that function to minimize the error in these differences. The variables involved are x and y, and those correspond to the columns on the data vector. The parameters to be solved are those values of a, b, and c that I don't know. The parameters are a, b, and c. Those are the parameters that accompany in this independent value, and multiplying multiplying this function and this function. And so I provide some initial values to those parameters, 2, 3, 1, just to get the solution started. The tolerance for the solution is this. The smaller you make this, the better the results in your solution. And so we have the data, the function, the variables, the parameters, the initial values, and the tolerance, and we're going to call the function fit with the data in this order: data, variables, or the parameters in this order, the arguments in this order: data, variables, function to fit, parameters, initial values, and tolerance. And we're going to store the result in a function called solve. If I put the equal sign here, sorry, you have to do control dot actually. That's going to produce some values a, b, and c. I'm going to do a control C here to eliminate. That means, so let me do that again. The control dot in front of here, control dot. It shows that I'm getting values for a, b, and c, but the result is a list where the values are given as a equal, b equal, c equal. Okay, so I'm going to delete this for the time being. And then I'm going to use the assign function. It's another function from Maxima. And when I use this one, what I get is the values that result from the right-hand side of these assignments. Okay, so now my list C includes these 3 values, which I am assigning to the solution here, and which I can now separate by making a lowercase a equal to C sub 1. This C sub 1 is C bracket 1, I'm sorry, uppercase C, bracket 1 equals, okay, and B is C bracket 2, and C, small c is big C bracket 3. So I got my values of A, B, and C extracted. And now I can redefine my fitted function as A plus BX plus tan of X ln of X. Now I'm going to bring back the original function that I defined to compare with the G function that is the fitted data. And you can see that A, which originally was 3.2, is 0.8645 in the method of least squares. B, that originally was 1.5, is actually 2.73. And C, that was originally 4.8, is actually now 7.552. So we did not just simply copy this, because remember we added some values to the function of X. And so we are getting the best parameters using the method of least squares. I'm generated here the fitted data by using a vector of G of XX. And these are the values that I generated earlier in my original data. You can compare here and see that they are not the same, but the tendency is similar. And so when I plot my original data versus G of X, the continuous line, I get my data trying to fit the point as best as possible. Okay, now I have another function called MSE. That means the mean square error. We provide data, the variables, and the function that I'm calculating, and I get the mean square error to be 2.2272. This by itself has no meaning. It just means that it's a small value. Then we can calculate the residuals. The residuals providing the data, the variables found, and the function fitted. And the residuals are obtained like this. The residuals are nothing but the difference between the original values and the fitted values. And as you can see, you're getting exactly the same results. And so those are the functions I wanted to illustrate for data fitting. Now, I started with this function, and I knew the shape of the function. And then I repeated the shape of the function here, trying to fit a function that will involve X times tan of X, ln of X. I'm going to change things here, and I'm going to try to fit let's say a quadratic equation. So I'm going to put bx here, and instead of ln of X, I'm going to put X squared. Now that changes the function to be fitted, and so we go to the solution, and we get different results in here. Now my function I'm going to fit here is going to be a quadratic. So I'm using a totally different function here. You can actually try to fit any function you want if you don't know the original type of function they're trying to fit. And a quadratic equation, obviously, it doesn't show such a good behavior. We may want to try a fourth order equation, in which case you'll have to add ABCD times X cubed plus, I'm going to use E times. The problem with E is that as my student thinks that you're talking about the base of the natural logarithm, so I'm going to put F. F I use that as a function, so I'm going to try M times X to the fourth power, for example. The variables are still X and Y, but now I need two more parameters here. Parameters D and M, right? And then I need to provide some initial guesses for those parameters. So I add two more elements here, and I'm going to put like a 2 and a 3 here. Tolerance for the solution the same. The solution has been found. Now I find five parameters, and I got A, B, and C, D. It will be uppercase C bracket 4, and the other parameter is M, C bracket 5. Okay. Now my fitted function is no longer just this one. I need to add D times X cubed plus M times X to the fourth power. Okay, maybe this will fit better my solution. And it does indeed. It does indeed, except for this peak over here that is a little bit exaggerated, but it does fit my 6 data points very well with this fourth order equation. And so this was the example I wanted to present For fitting data, you can follow this example to fit other data that you have. And for the time being, that will be the end of this video on Maxima plugin function fit and related functions.